Hello, testing, testing, 1, 2, testing, 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 testing. You guys need to turn off the light or not? Turn off the light? No, up to you. Can you see the screen? Yes. Okay. Because I also feel like if turn off the light, easy to feel sleepy. Yeah. Easier to sleep. Okay. If you can't see, then we can adjust again. Okay. So before we start, so let's do some exercise. I mean, brain exercise. Okay. Yesterday, what did we do? So what did we do yesterday? Anyone remember? What did we do yesterday? Vector space, subspace, and what else? Basis. Okay. Find basis. Okay, I want to pass this list down first before I forget later. Sun Kai Lu come yesterday, right? Make sure you sign for yesterday one. And Ling Yi, yesterday you can sign. Xu Yuchan here, right? Xu Yuchan, not here. Qi Yujin, Qi Yujin, Qi Yujin, not here. Okay, never mind. Okay, so what's the basis in Rn? What's the basis for Rn? So what's the set of vectors that span and linearly independent in Rn? What's the basis for Rn? Any idea? What's the basis for Rn? E1 to En. Okay, so E1 to En. So what does these are the we call the standard basis. Okay, and you have one at the I spot. So E1 will be something like 1, 0, and 0 all the way 0, 0 all the way until until 1. Okay, so why are these a basis? Because it's span. Okay, if you because it's span, so that means if you have x1, x2 up to xn, this is equal to x1 times e1 plus x2 times e2. Okay, so this one is span. So why are they linearly independent? Okay, so linearly independent. So if you set C1, E1 plus C2, or to Cn, En equals 0, or trivial solution. Okay, so if you look at so this is which is equivalent to solve uh, this matrix here. To solve this augmented. So diagonal, so this means only diagonal entries. Okay, so the columns are linearly independent because you have pivot at every columns, right? So, uh, so, uh, so you can see that this En actually forms a square matrix. Okay, if linearly independent, so what's the determinant of this? Can you calculate the determinant of this matrix here? Can you calculate the determinant of the matrix formed by E1, E2 up to En? Is this the determinant of this? Okay, one. Yeah, one. Okay. So what matrix is this actually? Identity matrix. Okay, good. So this is actually the identity. Okay, good, very good. Okay, so you can see that sometimes when we check for linearly independent, actually we can check the determinant is non-zero. Okay, they are equivalent under this. Okay, so if you found in the book, right, there's an invertible matrix theorem we skip in the class. Okay, but I did mention bottom part here in one of the lecture. Okay, so I suggest you go and read this. Okay, so this relates all the different ideas we learned together. Okay, for example, the column space, the null space, uh, linearly independent, span, linear transformation being onto one-to-one, and dimension of null space, dimension of column space, which is rank. Okay, relate all the properties together. Okay, I suggest you go and read this so that you can better understand what we are doing. All concepts are similar, just phrases in a different way. Okay. Actually, there's 18. Yesterday I count 18 different way to say whether a square matrix is invertible or not. Okay. Actually, they leave out one obvious one that we covered last time. So maybe I can add another QPQR. Okay. So you can say that if determinant A is non-zero, it is invertible as well. All the columns are linearly independent, or the column space span Rn. Okay. I suggest you can go and extend this table. Try and extend this table. See if you can find more equivalent equivalent properties. Okay. Try extend it, extend more. See how many we can get. Okay. For example, I already extend one of it. So if there's a 64 of you here, can everyone find one new one? Then we can add 64 equivalent properties in. Yeah. So I challenge you to extend this. I believe there's still some more. Okay. Yeah. So, but one thing I don't like to just teach method is I scared you just use the method without thinking. So every time when I do the question, right, I will tell you, oh, you need to check this two, and then this two, and then go and calculate. And I don't really care about the calculation part because I care about whether you know how to use the method or not. Okay, for example, a very easy misconception. So very easy misconception here. So last time I talked about one, so let's talk about second one. Okay, so pivot in a matrix. So every time when we talk about pivot in a matrix, is it a random matrix we're talking about? Okay, so let's say we have a matrix and an augmented matrix. So for example, let's say something like 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 0, 3. Okay, so let's say this is a matrix. And then this is an augmented matrix. Okay, so in the first matrix, in the matrix here, how many pivot? This is just a matrix. How many pivot? 3. Okay, so here got 3. But second, this is an augmented matrix. How many pivot? 2. Okay, so why one? Just why this 3 doesn't count as the pivot? Because in augmented matrix, what we care is the coefficient matrix. Okay. So if you don't know what we are solving, right? So you will tend to pick the 3 as a pivot. If you know what we are solving, actually we are solving the matrix part. Okay. This is the B factor that we always talk about, V factor, the constant part. Okay. So the story, the moral of the story is always know what you are doing. And if you don't know, you should point out here your doubt. Okay. So yeah. So you can see that in this case, right? This is not a square matrix. So if you want to check, so let's say if you want to check linearly, linearly independent or span call A. then you cannot use invertible matrix theorem again. You need to go back to the definition of linearly independent and span. Okay. So don't go and try and compute the determinant of this guy. You cannot compute. You can never compute. We never define determinant on non-square matrix. Okay. So make sure you know what you are doing. Okay. In some situation, it's more convenient. There's a lot of equivalent way to say the same property, but in some case, no. Okay. So always go back to the definition, and then everything will follow. Okay. Yeah. Okay. 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 So let's ask a last question before we go into a small question. So let's ask a small question before going to today's content. So what's the basis for Pn? What's the basis for Pn? Polynomial of degree at most n. What's the basis? Any idea? What's the basis for Pn? What's the basis for Pn? Early morning will torture your mind. What's the basis for Pn? So remember how you collect when you compare when you equate two equations, right? Okay. How you collect your coefficient? How you collect the coefficient? Remember? When you equate two polynomials, how you collect the coefficient? For example, minus 2t equals to something like that. Okay. So if you move to one side, right? So how you collect the how you factorize the coefficient? How do you factorize the coefficient? Same degree of t, right? Okay. So why are you doing that? Why in your mind you know that these things are together? Yeah, why? Why in your mind you want to combine this thing? Why not I combine 2 plus 3ct, something like that? Why not I do it the other way? Ever think or not? You ever think about it? You ever think about it? Why? Okay. It is because this guy form a basis for Tn, so that you can collect their coefficient. Okay. You can try and prove linearly independent and span. Okay, you can try and prove. We won't do it now, but later we will learn a new tools, and then using that tools, maybe it's easier to see. Okay. Okay. Is it wrong? Okay. Okay. So if you want, you can go and try using the normal way, the classical way, to show the linearly independent span. But later we will learn the new stuff, and then we can use that tool to help us to see why they form a basis. Okay. Is everyone get it? Got it? Any question? No? Okay. Okay. So remember that from last time, the vector space, after we introduced the basis system, we introduced the coordinate vectors. Okay, coordinate vectors for vectors. So we have seen that if the vector space, if Rn, we have different bases, then one vector can have different coordinate vectors. Okay. Does everyone still can recall it? Not, maybe I bring out the example again. So let's say we have R2. See now, yeah, R2. Okay. So let us write down two bases for it. So for example, I can pick 0, 1, 1, 0. And then I can pick another basis vector, 0, 1, and 1, 1. Okay. So let's look at one vector, maybe call it 5 and 3. Okay. So what's the coordinate vectors with respect to B1? What's the coordinate vectors here? 5, 3. Huh? What? 3, 5 upside down because of my arrangement. If I arrange the other way, then it's 5, 3. If I arrange the other way, it's a different way, then it is 3, 5. Okay. How about respect to B2? What do you get? -2, 5. Okay. So -2, 5. Yeah. Okay. So how do you verify it? So you just take -2 times the first vector plus 5 times the second vector. Okay. Yeah. Okay. Everyone on page. So you can see that vectors have different names inside the same vector space. Okay. I think this concept is relatively easy to understand. Okay, I give an example to one of your classmates. So you imagine you, right? Okay. So for example, Zhou Yi, right? Zhou Yi in this class, everyone know her as Zhou Yi. Okay, it's the same person. But if you go back to her family, and then what will her family call her? Maybe call her Ge, Ge, or something like that. Right? But it's the same person. Okay, it's the same person living in the same vector space, but a different name. If you consider different bases. Okay. So yeah. Okay, so this is if we generalize to general vector space. Okay. So in general vector space, we also have bases. Okay. After we have this basis, we also can express our vector in a unique way using this we call it a coordinate vectors. And this is similar to every vector space. So this is the special about basis. Why we need basis? Because this will give a unique way to express our vectors. Okay. You want? I think you guys are quite good in this example already. How about we skip this? Skip this. Okay, let's skip this. Okay, skip this. Skip that one. Skip that. Okay. Okay, maybe I give you some hard work to think first. Let's not do exercise first. Let's look at new stuff first. Okay. So you can see that what's going on here. Okay, so let's see. So let's roll out the diagram here. So given a vector space, okay, so the procedure is given a vector space with a basis. Do we have a basis here? Yeah, we got a basis. So let's say we have n basis. Okay. So by theorem, for any vector v in, okay, let's call the vector space v. Let's put it smaller. Vector space v. Okay. For any vector space in v, we can express uniquely in C1 up to Cn. Okay. So what this Cn, C1, Cn means such that x is equal to C1 times B1 up to, which is the coefficient you express in your basis. So okay. So you got the R2 example in your mind. Okay. So let's see actually what this is. So what are you doing? Let's look at this guy here. Where this guy live? Any idea what space this guy live? This is a vector, right? How many number inside the vector? N. So this guy live in Rn. Good. Okay. So this guy live in Rn. So what you have is I give you a vectors in a vector space. You give me an Rn. A vector is in Rn. Okay. So this is a mapping. Okay. So the relation. So we see that this map here, okay, is I give you a thing in a vector space, you give me a thing in a Rn. Okay. Does everyone accept? I give you a vector, and then you give me an Rn. Right? Is everyone following? Make sense or not? Does everyone follow? This one is very, very important because we need to use this for important result. Simple but very important. Can everyone see this is a mapping? So if I put a vector inside this square bracket, right, it will split, give me uh, a vector in Rn. Okay. Why doesn't seem convincing? What's wrong? What's wrong here? Why it doesn't seem convincing? Any question from you guys or not? Are you guys convinced? This is a map. Okay. So we got a mapping here. Okay. So on the right hand side is a vector space. On the left hand side is also a vector space. Okay. So between vector space, we have a linear transformation. Okay. Between vector space, we can define a linear transformation. So we can check whether this is a linear transformation or not. Right? Okay. Do you still remember how to check whether something is a linear transformation? Any idea? Check linear transformation. Okay, we are trying to put everything we learned together today. Okay. So what's the check? How to check linear transformation? What's the two property you check? One is the mapping preserve uh, vector addition. Second is preserve scalar multiplication. So what does this mean? So for the first one, we want the linear transformation add on x plus y is equal to tx plus ty. Can still remember, still recall, and recall this. Okay, and the next one is t times cx is equal to c times tx. ctx is equal to c times tx. Okay, can recall this. Okay, so if you satisfy these two property, this is a linear transformation. Okay, so the claim is claim meaning what I say is true. So the claim is this mapping here is a linear transformation. So the claim here is this is a linear transformation. Okay, so it satisfies these two properties. So if you do you want to see or you want to try yourself? You want to see why? Why this mapping is a linear transformation, or you can try you want to try yourself? Hello? You want to see? Okay. Okay. So okay. So the claim is, let's prove this claim here. So claim is a linear transformation. Okay, so proof for one. Okay, so let's take for any x and y in my vector space. Okay, so what can I do? We can write our x and y as a linear combination of our bases, right? Okay, this is the thing we are given. Okay, we got a basis. We can express our vectors in a linear combination of our bases, because this is what bases do. Because bases span. Okay, and this is a unique form we have. And y maybe have d1, d1, b1, 2, dn, bn. Scoring. Stuck. I think the table got something wrong. Let me check. Suddenly disconnect. I have to restart the iPad. Because not connecting my pencil. Sorry, I need to restart my iPad. It's not connecting. Right, let's return. Let's see. Okay, so we start here. Okay, right. So we have these two. We can write uniquely express them. Okay. So what is the coordinate vector for x plus y? So what we do is we just add up the two right here. No, polynomial, I mean vector. Yeah. And then we add one plus. Okay. So when we do this, we can do factorization, right? Okay. So we can factorize the coefficient for B1. Okay. So remember from just now, we said that factorization is there's some kind of basis behind you. So actually we are combining the coefficient of the basis. Okay. So what's the coordinate vector for this guy? So the coordinate vector of this guy is just the coefficient. So it's just C1 plus D1, D2 plus D2, Cn plus Dn. This is definition of uh, by definition of the coordinate. Okay. So what's the coordinate vector? Coordinate vector read out the coefficient in the linear combination of bases. Right? So you write your vectors in terms of the linear combination of basis vector, and then you read out the coefficient. Okay, is that okay? All right. Okay. Okay. So we haven't done yet. We haven't done yet. So we want to show what? Okay. Let me go back to our goal. Want to show what? Want to show bracket of x plus y b is equal to x plus bracket. Okay. So how about the right hand side? Okay. So how about right hand side? So how about bracket x b and bracket y b? Okay. So what's the coordinate vector for C1b, C2b up to CNB? Okay. So what's the coordinate vector for this? Read out the coefficient is just C1, C2 up to Cn. Okay. How about B, about Y? So the coordinate vector for Y is just read out the coefficient is just D1 up to Dn. Okay. So can you see now why the coordinate vector of x plus y is equal to coordinate of x plus the coordinate vector of y. So on the left hand side, you have the vector that has C1 plus Ci plus Di. Okay. On the side, you have Ci's, all the Ci first, and then plus all the So is the left hand side, right hand side equal? Yes, right. Okay, because this is true by definition of addition in R. So this is why we define our vector addition like this. So it's quite useful. Okay. So we have that the coordinate vector is a mapping and it preserves vector addition. Okay. For scalar multiplication, okay. So for scalar multiplication, what do you do? So next, we want to show square root cx, not square root, square bracket cx is equal to c times bracket x. Okay. So we already write cx in a general form. Let's keep using this. Okay. So what is cx? Okay. Last time we know that it is just multiply everything with c. Everything up to c, c, and b. Okay. So in this case, what is the coordinate vector for cx? So to ask about this, okay, you see, so this b is very important. Okay, this means that you need to express your vector in terms of vector in basis. Okay, so I already done this at the top. So which is this? So I put this in here. Then this square bracket will eat these bases because under this basis we know where they correspond to. So we just get the coefficient of CC1, CC2 up to CCN. Okay. And then on the other side, what do we have? On the other side, we already computed. So which is this one here? Okay. Here again. So get this. So on the other side, we already computed before, which is this C1 up to Cn. Okay. Weird. Okay, let's do it again. So let's compute the coordinate vector for x. So what is x in terms of b? We already write it down here. So which is this? C1 plus C1b1 plus C2b2 and so on. And then if we read out the coefficient, it's just C1 up to Cn. Okay. So if you want to check this this equality here, okay, we want to check this equality here. So what do we have? On the right hand side, we have CC1, CC2 up to CCN. On the okay, this is left hand side. On the right hand side, we have C times the coordinate vector of x. Okay, so is this true? This is true by scalar multiplication in Rn. Okay, so we have a linear transformation between vector space. So that means whatever you do on the left hand side, you add the vector first, and then you transform it. It's equal to you first transform it first and then do on the right hand side. So what does this mean is it really doesn't matter where you do the operation first. Okay. Between vector space with, let me see. So let me write down what I want to say. So if you have a vector space, basis V1, Vn, and another thing is Rn. Okay. So we have one map between them, this coordinate vector. Okay. There's a map between them. Whatever you do on the right hand side, you can do on the left hand side. Sorry, on the left hand side, you can do on the right hand side. Okay. But can we really, how to say, can we really go back and forward? Yeah, because just now we only have forward map, right? We only have one arrow going forward. Okay, we can only go forward. Can we go backward or not? Okay. We want it to go backward. So one thing to check is this linear map 1 to 1 and onto. Okay. So if it is 1 to 1, then whatever I do on the vector space is the same as what I do on the Rn. If it is onto, whatever I do on the Rn, I can put it back to the vector space. So if it's 1 to 1 and onto, it doesn't matter where I live. The two are similar in terms of vector space operation. Okay. A bit weird, is it? Okay. How about let's check whether it's 1 to 1 or onto or not. Okay. So to check the linear map is 1 to 1. We just need to know if x is a, so to check the linear map, okay, let me write t here. To check t is 1 to 1, we just need to know if tx equals 0, then x is equal to 0. Okay. Just recall what we did last time. As equals 0, then x have to be 0. So the null space is only 0 vector. Okay. So, so this one is important. Let's do it. Okay. So suppose this one is so now suppose 3 is equal to 0. Then we want to show x is equal to 0. Okay. So if so if you what does the first step here mean? Okay. What does this mean? This means what? The coefficient of x when you express in terms of the basis is all 0. Okay. Since x b equals 0, x is equal to 0 times b1 plus 0 times b2 plus all the way to 0 times b. Okay. Which means x is 0 vector. Okay. Because why? Because this because okay, let me write it down. So the coordinate vector of X is C1 up to Cn, where X is equal to C1B1 plus C2B2 up to Cn. Okay, but we have this coordinate vector here equal to 0 vector. So meaning C1 up to Cn is just 0. So you can plug it in and then you get X equal to 0. Okay, so T is T. So T is 1 to 1. Okay. If you are stuck, if you can't recall, you need to accept what I say here first. Okay. So to show that T is 1 to 1, we just need to show Tx. When Tx is equal to 0, X must be equal to 0. Okay. If we have done this, then that means T is 1 to 1. So if you wonder why 1 to 1 is equivalent to this, you need to check back to the note. Okay. Okay. So how about the next one? Is it onto? Okay. So what does it onto mean? So for any x in Rn, okay, we need to find, okay, maybe this one I put another one. For any y, okay, use y. For any y in Rn, we need to find x in V such that this part is for onto such that Tx, okay, this one specified to be such that Tx is equal to what? Okay, so let's write y equals to y1, y2 up to yn in R. Okay. Can you find, the question is, can you find an x? Can you find an x such that if you read out the coefficient of your x relative to the basis, you will get y. Let you think a bit. Can you find an x such that when you read the coefficient, you get this y vector? Can you find such x? Can you find such x? Can you find such x? So what do you need to put in front of your basis such that when you read the coefficient out, you get exactly y1 up to yn? So what do you put here? What do you put there? You put just y1 up to yn. Yeah. So that when you read this coefficient, read the coefficient of the vector x, you get y1 up to yn. Okay. So what does this mean? Okay. Okay. Let's have some picture in your mind, right? Let's put some picture. So you have V vector space. You also have Rn, okay, and then you have a linear mapping. You have a linear mapping, the coordinate vectors, okay. So it is 1-to-1, meaning what? Meaning everyone in V has a unique representative on the right hand side. Okay. Not only that, you for every Rn, you also can find another guy back in V. Okay? So this means there's a 1-to-1 correspondent. Okay. So whatever I do on the left hand side, the vector space, is the same as what I do on the right hand side, Rn. Rn, we already know how to do computation on Rn, but vector space can be general, like the polynomial, set of polynomials, set of infinite sequence, or set of anything, as long as the vector space defined. But we have surprisingly found a map between a vector space and Rn, given that this vector space, right, is equal to the span of V1 up to Vn. Sorry, I used B. I should use B. V1 up to Vn because we used B just now. Okay, so if you happen to know your vector space is V1 up to Vn, then this space is this is what we call a isomorphism. Okay. In discrete math, we learn about graph isomorphism. In this case, it's a vector isomorphism. So you have a, what does it mean by isomorphism? It means that you have a, wait, let me write it down. So it means that you have a linear transformation, which is 1-to-1 and non-to. Okay. So because I think you guys are coming from various discipline like accounting, XWE, DMT, IBU, and what else? Hence, okay. So if your discipline need to collect a lot of data, okay, you need a lot of variables. So these different variables will form a basis if they are independent to each other. Okay, and then you can use these variables to form a vector space. Yeah. Okay. So you can imagine the variable become vector space. If they are independent to each other, then they are linearly independent to each other. If they are dependent with each other, maybe you can just throw away. No need to see it because you can see the result from, you can see that variable from the others variables, right? So you can reduce your variables. So if you have n independent variables, then you have Rn basically. Okay. Okay. How about we stop here first, and then later we'll see how to use this, and then we go to the next section. Okay, let's come back at 9908. 哎，
就是
嗯
是刚才就是你看的那个图，
可以，怎么说？
它从这儿
嗯哼
map 到那儿，
，yeah，没有
然
错
后为什么那两个又能 map 回去？
啊，因为它 on to，
然后出的我理解的啊，就是从这儿到这儿才行，就是 y 嘛
对，
，y 它还能回到，这反回事儿感觉。
没有错，反函数就是如果这两个条件符合的话，就有一个反函数，或者其中一个就有一方面的反函数。有反函数不是有两个？OK，等一下，要不
没有见过
然加
这样的东
是吗？
西，就是也算
对
on
对，
to 嘛，
再来一次，
就是
发现，嗯
我之前一直 on to 就是
嗯，
所有的 y 都有一个 x
对
来表示，
对，
但在刚才那个图里边儿，它有两个 x，y 的值是 x，是它来表示 x 的，就是就是同样的一个 x，它映射到 y 里边儿是一个，然后 y 里边儿另外一个又映射到这个 x，就刚才那个图的意思。
嗯哼，然后
就我之前想的不太一样
跟你之前想的，
，onto 的
你怎么想？
是哦是同一个 x 啊，那就是每一个 x 都对应到这儿的一个 y，
嗯哼，
这儿的一个 y 又对应到这儿的一个 x，就是这它不会对应到它这儿，但是它这儿有个对应，这样也算 onto，
就是可以有不同的东西对应到同一个，对对对，没有错，
只要就是
没有错。
两边就是一对应，啊，这肯定是一对应 one to one，
然后，
然后只要它们有关系就 onto，
嗯
虽然说这儿没有就是映射到全部的它。
嗯哼，
但是它这儿正好那俩就是剩下那部分映射到了它这儿，
所以
就自己上去，这算
你说如果有两个公数一定要这边培育是等于值。onto 的意思就是说，每个这个都一定要至少一个，
我记得是就是每一个它都有，对，每一个它都有一个它来对应。
对，至少一个，
那它是你
哎，
就说
不是至少一个呀，就一个，然后，
对，至少一个，
然后，
嗯，
对，至少一个，
但但是这两个没有它来对应，是它是这样的两个是它来对应。
没有，意思是我的哦，我这个图的意思就是说，假设你有一个 one to one 的 map。
嗯，这是 one to
OK，
one，都
one
是
to
one
one
to
的，
one，
然后你又要 on to，假设说这里还有更多的东西嘛，其实它还有更多的东西可以对应到，这个还是里面的东西，其实
就是看这个箭头怎么指了，这个是这样插的，然后我认为应该都是这样，
看一下，
就是只有 x 到 y。
哦耶，啊，对，但是我主要要画这个箭头是为了说，嗯，就是说可以回去的意思哦，就 OK，所以它的 map 其实就是它的 map 其实是这个
对对对
箭头，
啊，对。
但是我故意画这个蓝色箭头，就是因为当你是 one to one 和 on two 的时候，你就可以回去。耶，因为反正我也没有很仔细在说在干嘛，只是我想有一个概念，但是呀，全部箭头都是完全，这个意思来讲，但是差不多的一样，因为那时候我们是说 graph 的，然后这次我们是说 vector space。
做一个东西，
一
就还是
在不同的世界里的一
我高中都没怎么理解什么叫两个大水平面。
对，是不是？呀，对吧？这个可能他怎么推的？这个为什么一定成？你跟说。
那你看那个结论，
然后，
看那个
然后我认为这个也可以互推，可以。这两个学校，就是这个 x vector 嘛，呀，对，是 one to one，对，这是 one to one 的意思。这是 one to one，对，因为如果你看，因为为什么你反着方向写啊？什么反着？ 就是这个。为什么你通常我们是这样写，为什么你这样写？
为什么能够交结合律？
对，
为什么能够分配律？不能分配律，
什么叫分配？
这样的，你不能把它展开讲。
x 跟 c 都是矩阵。
嗯，
可以，我觉得可以，
会觉得，
可以啊？
会觉得，
什么你觉得？
那我不知道怎么就
真的方法就是你怎么乘你的那个 matrix 嘛？就是当你在乘 matrix 的时候，你就是在乘很多个 column vector 一起乘。
先把 x 和 c 把这变成 x，
这是 column vector。对，对，嗯，但是你
a 也就要拆开了，
A 不需要拆开，A 可以整体看。
整体乘上一个一个单独。那
区别。
不对啊，对，
然后这个其实就是one to one 的意思，就是因为这个等于零等于里面那个等于，它跟 one to one 是一样的意思。因为这个东西是可以的，所以是这整个东西，就是 y 的话，ay 等于零代表 y 等于零，这是 one to one。对，
这个东西是在这里面是什么？
哎，不是哎，这个问题很好哎，
在这个里面，
这不是。
那这里面元素长什么样？然后这些东西里面都是成员是长什么样？它跟那个 vector space 是什么关系？它算是 subspace，是 vector space 的 subspace，还是什么？
不是。
所以里面成员是什么？
什么时候成员？
就是里面有什么元素，它的元素长什么样？
哪一个因素？
就比如23，它里面是括号，然后这样的，比如这个就是化学，然后22是这样的，就这样。那
它 space 的话一定长一样的，只是它是其中一个 space。
也是一个括号，subspace 本身代表的含义就是子空间，所以它是不是肯定要有一个主语，比如说23、22。
对。
然后这个是 vector space，
对。
vector space，所以是包含了2、1，单独就23就是
是什么？
vector space，
是，这整个
这都分别是 vector space。
对，
然后这个 calling space 里面的函数也是根据那个，也是这样一个括号，
是啊，
都，就是也是一个一个下来，都给你称
知道。
啊。那应该是什么呀？
功能 space 是指，哎，等一下，我再回答你。OK，等下我回答你。
还有一个老鼠，
还有，
还有，base 可以化简吗？这个我觉得可以，我没有问题，可以。
哎，现在是这样多问题，把它放上去，
然后
把它放上去那个上面，我先提前看了，我就可以提前准备到。
我这个两个能不能化简？比如我把它化成100，或者010，比如说，
不可以，
为什么不可以？
你直接看嘛，这两个写不出这两个，
就如果能写出来，
如果能就可以，
那所以到时候随便画。
不可以随便，写不出你就完了。这样，
那是不是还
有一个，
matrix 乘
啊，
matrix 乘 column 的，就是把它看成那个它的排列的线性，
然后，
也可以，就是
我要准备开始啊，怎样？
那个题它就是好像是这个把这一列，然后分别乘上它的几点，叠旁的，
对，
也可以这么做。
哎，这个
不是把它乘在，哦，
你是说把这个再拆开，
不是拆成每个元素的，
拆成两个，
拆成 volume 啊，
对，拆成
好像也可以，
就是 matrix，
可以的，可以的。
它转置为什么主元不对？
下次放在那个题目上面。现在我有很多东西要做，
放在哪？
放在那个木的上面。等一下那个3000个，然后我提前看，我提前准备。啊。
放上去，不然我现在我要做起来，我要有的螺丝头就奇奇怪怪的。你先放上去先 OK，我会解决。Hello。
Okay, so yeah, just now I draw this arrow, right? Okay. Really, this is a map going from the left hand side to the right hand side. Okay. So why I draw this blue arrow is if your map is 1 to 1 and on 2, you can find an inverse map going backward. Okay. You can find an inverse map going backward. So there's another map going backward, inverse map. And yeah, there's an inverse. So how should I do it? It's an inverse map like this. Okay, going forward, going backward. How to find the inverse map is actually defined by this, by the onto part. How you check the onto part. So I give you an Rn, you can give me a vector. Yeah, you give me an Rn, I give you a vector. This is the how you go back. I give you a vector, you give me an Rn. Sorry. You give me an Rn, I give you a vector in the vector space. So this is how you go backward. So this one address another question from Seng yesterday. Seng, right? Yeah. So yesterday she complained. Okay, she complained for this question. What to do all this nonsense stuff? You see? Why not just get this matrix out? So how you get this matrix out? Can you recognize that this matrix here is actually the coordinate vector for P1, P2, and P3. Okay, let's write this down. So this is the world of a polynomial of at most n, right? Okay. So the basis of Pn is what? Is 1, t, and t squared. Okay. So what is the coordinate vector for P1 in this case here? Anyone can read? What's the coordinate vector? Should I copy? Let me copy this. What's the question? Okay, let me copy these two and then we do it today. So let's redo the question from yesterday, okay? We call the question here. So we got 3 polynomial and then we want to determine whether this 3 is the basis of P2, okay? Just now we realized that there's a connection between P2 with let me make things smaller and then make this thing disappear. Later we're gonna use it again. I'll make it smaller. Let's make some space. Size. Okay, and then we make the thing we do yesterday a bit smaller. Okay. So this is what we did yesterday. This is what we did yesterday. So from today, we learned that P2 from today, what do we have? So P2 has a basis. Okay. P2 has a basis. What's the basis of P2? Is 1t and t squared. Is everyone okay with this? 1t and t squared. This is what we said in the start of the class, but I can show it. So this is the basis of P2. And then we show that you have n bases for your vector space. It is isomorphic to Rn. Okay. So in this case, this is isomorphic to, let me put this, isomorphic to R. You have three vectors here. So it's isomorphic to R. What? You have three vectors in your basis, so it is isomorphic to R3. Okay. 3 bottom or top. Okay. So what's the isomorphism? The isomorphism is given by the coordinate vector, right? Okay. So if you read out the coordinate vector of P1 with respect to B, what do you get? What do you get? You get 1, -2, and 0. Okay. How about P2? What's the coordinate vector? -4, 1, and 7. What's the coordinate vector for P3? -2, 1, and 5. Okay. So you can see that the matrix here, okay, is actually the coordinate vector for your polynomial with respect to this basis here. Okay, everyone see it? Okay, so you see, we introduce C1 into the game. Okay, and then after we factorize with respect to t squared and 1, we throw away C1, C2, C3 again. Okay, so what we are doing, we're actually doing this coordinate vectors here. Okay, so from this matrix here, right, there's some more condition it encodes. Let me move. So you can, last time we see that the column record the solution, right? The variable C1, C2, and C3. How about row? In this case, the row here encode the basis. So 1 t and t squared. That's it. So you can see 1 for 1, the coefficient is 1, -4, -2. For t, it is -2, 1, and 1. For t squared, it is 0, C1, plus 7, C2, plus 5, C3. Okay, so now the row also have meaning now. Previously also have meaning, but it's just position. But now they are somehow, we call it graded. This is the degree, right? Degree of the polynomial. So they are graded by this degree. So in this case, they are graded by the degree of. Okay, so the row have meanings now. Make sense? Making sense? So the row is graded by the degree of polynomials, and then the columns are the usual variable for your solution. Is it okay? Yeah. Okay. So yeah. So really, after we have learned this coordinate vector, you can no need to start from scratch. You can just start from here. But make sure you compare to the right things. Okay, maybe we do some example and then see how to use it. Let's do some examples. So let's say, okay, this one is the usual one, right? This is the usual Rn, R3, okay? So this is left as homework. Then we will compare answer after I pause out. But this one is a bit special. Right? There's one thing I want to show you, but Maybe I will show in this then. Okay. Okay, so let's look at this one. Okay. So let's look at this question here. So consider the polynomial P1, P2, and P3 in P2. So P2 is our vector space. And let our basis be P1, P2, and P3. So they form a basis. So you want to show that it is really a basis. And then find the coordinate of PT equals to 17 minus T plus 2T squared relative to B. Okay, so let's recall what we want to check and then we see what technique we want to use. Okay. So to show B is a basis, what do you need to check? So you need to check two things, right? So you need to check that. Check B is linearly independent. B is B span and B span are P2. Okay. Okay. So from just now, what do we learn? We learned that what? We can take coordinate vectors for P1, P2, P3. Okay. So what's the coordinate vector for P1, P2, P3? P1, what do you have? You have 1, minus 2, and 3. Okay. But this one we take based on with respect to relative to the basis 1 T and T squared. So if I change this basis, right, the coordinate vector will change as well. Okay. So this case we choose the basic one. So and then P2 we get 0, 2, minus 1. Good. P3 we get 3, 1, minus 1. Good. Okay, so I get these three vectors. Okay. So what we can do is we row reduce this guy. Okay. Let's see we row reduce this guy. What do we get? Okay. Let's do some quick mental calculation. You help me to check. It's 5. Okay. And now 7. Right. 3 minus 1 minus 1 minus 9 minus 10. Right. Okay. And then what can we do next? 103 127 0. Change the third row to the second. Okay, I follow you. Okay. 0 and minus 17. Okay, so you can see that we have a pivot on 3 part 1, 2, 3. Okay, so we can say that the columns are linearly independent or invertible, but we care about linearly independent first. Independent. And they also span because you have, so they span and span 3, right? Because you have every row you have a pivot, every column you have a pivot, right? Okay, so far okay. So far okay. So far okay. Okay. So R3. So in this case, we can deduce that since P2 and since P2 is isomorphic to P by the coordinate vector map, okay, P1, P2, P3 are also linearly independent. So linearly independent span P2. Okay. So whatever you do in P2 is the same as what you do in Rn using the coordinate vector. Okay. Yeah, this is the result of why coordinate vector is 1-to-1 and on2 is important. Because whatever you do on vector space, any vector space with n basis vector is the same as what you do on Rn. Okay, so you can change the question into Rn and do row reduction. Okay. Yeah. Okay. About the next part. Okay. Okay, how about the next part? So let's say we want to do the next part. So let me make this one. So how about next part? So you want to find the coordinate of PT with respect to B. Okay. Okay. Something weird here. So actually, let me change this to BS. Okay. Because we already have B here. So I don't want to like clash notation here. Okay. So I put a BX with this because this is a standard basis. I put BS. Okay. Is it okay? So I put a BS here. I don't want to clash with this B. So in this, from this question, you can see that there are two bases here. Okay, there are two bases here. So two different bases. Okay. So what? So this one is a BX. So let's find B. 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 Find the coordinate for PT. So I want to find PT. PT with respect to B. So PT is 17 minus T 2T squared. Okay. So what can we do? What can we do? So what can we do is we set up the same matrix. Okay. Set up the same matrix. If I just tell you the step, you are like blur. If I don't go, so in your mind, you should go through the coefficient thing. You get what I mean? The coefficient. So, okay. Maybe I just write it down, but I don't expand it. Okay. So what does this mean here? Okay, let's just spell out what this means, right? Okay. So this means that you need to write 17 minus t. Okay, or let me write pt. pt as c1 times p1 t plus c2 times p2 t plus c3 times p3 t. Okay, but you can see that this p1 is a weird thing, so it's a long thing. Let me how to copy this. Okay, let me get it from here. So 1 minus 2t plus 3t squared plus ct times 2t minus 3t squared plus c3 times 3 plus t minus t squared. Okay, and then you need to express this pt in terms of this guy. Okay, so this is what we did yesterday. So we go and expand it, and then we collect the like term with correspond to degree 1, degree 0, and degree 2. Okay, the coefficient. But today we can just use the we just set up the coordinate vectors. So we can set up the vectors. So really what we are doing is we can put P1 T. Okay, I think this one is clearer. So BS with respect to BX, and then P2 T. Okay, I think this one is better. So what we really want to do is we can show that we can use PT. We can use this method to find PT with respect to BX equal to C1 times PT. Okay. What we do is we just read the coefficient of the right-hand side and left-hand side with respect to BX, the standard basis in my P2. BX. Okay. Apply the coordinate vector on both sides. Apply the coordinate vector on both sides. Okay, why can I do this? Because why can I do this? Because let me write down. Because it is a linear transformation and it is 1 to 1 and 1 to. Okay, you need all these conditions so that you can apply the function to the vectors. Okay, so instead of checking the vectors in your vector space, you can check it on Rn. Okay, so in this case, you reduce your question to checking on Rn. So what I get here is the vector equation becomes something in Rn, which is C1 times the vectors times P1 T dx plus C2 times P2 T dx plus C3 times P3 T dx. Okay, so when you see so many notation, right, don't be scared first. Okay, so what happened here is everything here is in R3. So it's a vector in R3. So you got another vector equation in R3. So you have a vector equation in R3, you can do row reduction again. Okay. Yeah. Okay. So what you do is you turn the question in general vector space into a question in Rn using the coordinate vector. Okay. So in coordinate vector, you can just do the row reduction again. So here you put what? A 17 minus 1, 2. And then the solution you get is what you want. C1, C2, C3. Okay, makes sense? Makes sense? Okay. So the key, I think the key here is this one. Okay. So the key here is really this part here. So this part is good. Very important part. Okay. So you can turn the question into something in Rn. Is that okay? Okay. So the key from the first hour is you can change question in general vector space into Rn just using the coordinate vector. Okay. So coordinate vector, be careful you what basis you pick here. You see, I always pick the standard one, standard basis, because that's the easiest one to work with. Okay, standard basis. Okay, is it okay? So in this case, right? Okay. 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 So the next thing is dimension of a vector space. Okay. So I think quite often you guys come and ask me what's the dimension is. So dimension is nothing special. It's just we got a basis. We just count how many vector inside there. It's really so. Let's say, for example, basis of co-A. Let's say we write it as 0, 1, 0, 1, and then 0, 1, 0. Okay, so let's say this is the basis of co-A. Then the dimension of co-A, or we call it a rank, okay, is just 2. We just count 1, 2. Okay, this is the dimension. So let's say we have a vector space and then have a basis B1 up to Bn. So then any set in V sorry. So the dimension of the vector space here, so this means that this dimension of V is equal to n. So you can see that the 1, 2, 3 here, we just count the n. Out to n. So the dimension of V is n. So there's a theorem we have here is then any set of V that contains more than n vectors must be linearly dependent. I think this one, if you can recall, this is quite obvious for R3, right? So not R3, I mean for Rn. This is obvious for Rn. Obvious for Rn. Because let's say for R3, okay, let's say for example in R3, in R3, okay, R3, how many bases? So just now we said that this is span of E1, E2, and E3. Okay. In particular, if you put them together, it's just the column of your identity matrix. Say I put more set into this set here, E1 up to E3. Okay. more set into the set here, more vectors into here. For example, this. For example, this. You can see that this set is actually linearly dependent. So how to check from linearly dependent? So you will put it into matrix again, right? Okay. So inside this matrix, what's the number of pivot you can get at most? For this case, 3. Because this is a 3 times 8, 3 times 5 matrix. So there's at most 3 you can get. Okay. The other 2 must be linearly dependent to the other. Okay. So this is what it means. If you have your matrix, if you have vectors more than your bases, then it must be linearly dependent. Okay, this is obvious from Rn case. So for general vector space, right, you can reduce to Rn case. Okay, so for general vector space with basis, very important. Not infinite base, not infinite case, but with the finite case, finite basis case, Bn, we can reduce the theorem to Rn case just by applying the coordinate vectors. Okay, so just by applying the coordinate vectors, then everything we solve is really Rn case. Is whether a number of column is greater than number of rows. Okay. So from general vector space, applying coordinate vectors, we can go to Rn case. It's the same. It's really the same. Okay. But the details, if you want to look at the details, you can look at the textbook. But what it says is, after you apply coordinate vectors, what you are dealing with is what you do in Rn. Okay. Okay. So this means that if we have a vector space with a basis v1 up to vn, then any set of v that contains more than n vectors must be linearly dependent. Okay. Okay, next is this is very important before we go to the next definition. So it might seem easy. It says that if a vector space V has a basis of n vector, so this means that the dimension of V is, so your basis got n vector. So the dimension of V is, okay. Then every basis of V must consist of exactly n vectors. Okay. So this is another question. Some of you ask me, if I found a basis of co-air, can I add more basis into more vector into a basis or not? Cannot. If you add more, that means there will be linearly independent, linearly dependent. Okay, so you cannot change the number of bases. Okay, any vector space include co-A, column space, row space, null space. Okay, you cannot change the number of your bases already. Okay, so how to prove this? Actually, this is an easy proof. So because every basis must have as consists of exactly n vectors. So suppose we have two. Suppose we have two bases, v1, v2. Okay. So let's say suppose v1 and v2. If v1 has n vectors, okay, then B2 has most n vectors and most n linearly. Let me put, wait. Suppose we have two set of B1, two set of bases, two set of B1, B2 bases. Okay. If B1 has n vectors, then B2 has at most n linearly independent vectors. Okay. This is what we achieved by previous theorem. Okay. Because we said that if a vector space has a basis of B1 up to Bn, then any other vector space contain more than n vectors must be linearly dependent. So it must only have at most n. Okay. How to show there's exactly n? How to show there's exactly n? How to show there's exactly n? Or you mean if it cannot span? It cannot span? Yeah, there's one way to see it, which is what I gave last time, right? Let me see if we have another way to see it. Okay, let me see. Okay, yeah. So yeah, you can see it that way. So if sorry, if B2 has less than n linear, wait, let me see, n more, sorry, if a linear in the, if B2 has less than n linearly independent vectors, then it doesn't span V. So why is this true? Why is this true? Why is this true? Why? Is this obvious or not? Why is this true? So if less than n linearly independent vectors, then it doesn't span V. Hmm? Yeah. See, so one way, so there's one thing we see from the book. It says that since B2 is a basis and B1 is linearly independent, then B2 has these n vectors. So these two should connect each other. The idea, since if B2 has less than n linearly, then it doesn't span. Since B2 is a basis, this means it spans the vector space, and also it is linearly independent. So basis means since you have a basis of n vectors, so you must be able to express the n vectors using the basis in B2. Okay. And B1 is linearly independent. Okay. So we already suppose. Okay. So we already suppose B1 as okay. We already suppose B1 has n vectors. And then they are linearly independent. Okay. This means if I can express V1 up to Vn, okay, using maybe this is W1 up to something, I don't know, maybe Wm. Okay. Each of them has a different, so I should say, okay, should I, okay, make it small, and then we write more stuff. Size. Okay, so if we do the coordinate vector, if we express V1 in terms of V2, okay, they should all different. They should be all different. Be all different. Then by this means that V2 have to has at least n vectors. Otherwise, you cannot achieve this. Okay, is it okay? Yeah. Otherwise, you cannot achieve this if you don't have n vectors, because we reduce the question to Rn again. Okay, because if you have less than, for example, if you this means that okay, so let's say where is n? N is on, I think so. Is here, n is here. So if n is less than n, what happened? M is less than n, you will have inconsistent system. Okay. Is it okay? So if m is less than n, then you would have inconsistent system. So what we do now is we translate the question to I. Okay. So if we have less than n vectors in B2, then we cannot express everything in B1. Because we will have m less than n, then we will have inconsistent system. Okay. I will write out in details in the lecture notes later. Just ask if you want. Okay. Then So what do we achieve is if you have a vector space with n vectors, if you try to find different bases for it, it is still n vectors. Okay. So what we get is actually a vector space. Okay. What we get is an invariant of this vector space, which is the dimension of the vector space. Dimension of the vector space. So dimension of the vector space won't change. Okay. Given a vector space, I have a dimension. So this dimension won't change. This is the invariant of this vector space. So this is what we call the dimension of the vector space. So let's say if V is spanned by a finite set, then V is set to be finite dimensional, which is dimension of the vector space, the number of vectors in a basis for V. And the dimension of a zero vector space is 0. If a vector space is not spanned by a finite set, it's said to be finite in finite dimension, infinite dimensional. So for example, what we have seen, what kind of vector space we have seen? Okay, let us draw something. So here is a vector space, and then here is a number. Okay, number. So we are seeing something like R2, R3, right? So we go here, we take dimension. So R2 is 2, R3 is 3. So in general, Rn is n, okay? Number of standard bases. So we also have what? We also have Pn, the number of the set of polynomial of degree at least n. So this is also n, okay? Number n. So what we have to do? We have to do the set of infinite sequence. Okay? Set of infinite sequence. What's the dimension of set of infinite sequence? Okay. Last time I said that this is actually Rn, R infinity. Okay, so this is actually infinite dimensional. Okay. Also, we have learned set of real value function. Real value functions. Okay. Actually, this is also infinite. Okay. So out of few things we learned, we have infinite. So you cannot write down the basis. The basis is forever and ever. You cannot list all of them down. Okay. So yeah, so actually this is what my research on something like this. So we have number, we want to attach a vector space to the number. Right. Let me tell you this story first before we break for quiz. Okay. So in my research, we got numbers, interesting numbers, and then we attach some vector space on the number. Okay, why? Because between vector space, there's map between vector space. We call it linear transformation. But between number, there's no map. Okay, so this gives a new way to think about a number. Okay, there's a thing attached to the number. Okay, so what do you think how natural numbers come from? Okay, why human create 1, 2, 3, 4, 5, 6, 7, 8? Why do you want to count things? Okay, for example, in the old time, right? So there are two shepherds. Okay? There are two shepherds. So both of them rear a herd of sheep. Okay, let's draw a sheep like this. Okay. Just draw the body of sheep. Okay, so one day the shepherds want to ask the other shepherds, want to compare their sheep. Okay, how do you compare? So you try to form a bijection. Okay, bijection meaning one-to-one and onto map. So I got one sheep, you got one sheep. 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 But I got one, but you don't have the other one, right? So there's no bijection form. In this case, If you can count, then this will make it easier. For example, I have 6 sheep here. For example, you have 5 sheep here. So I have one more than you. Okay? So this number is an invariant of the sheep. Number of sheep. Okay? But every number corresponds to different sheep. Does it make sense? Okay. Does it make sense? So yeah, so whenever you do mathematics, right, you should think about what this number represent. Okay, in different space, in different subjects, the number will represent different things. And then in the end, when you do 6 minus 5, 6, they are just computation. Okay. Yeah. So when you put into different situation, there will be different meanings to the number. Yeah. So today we will stop at a dimension, and then we will, let's see, I will see if we need to do some exercise to help us understand this topic. And then next time we will do exercises. And then see if there's some useful step I want to share you, then we will do it next time. Okay. Uh, any question before we break? I know you guys got a lot of questions, but I don't want to ask in the public. Okay, let's take a break until 10:10, and then we come back for quiz. Yeah. Okay. Jory 有人 sign it. I think most of you are back. We still have time if you want to ask anything. You want to ask. You can ask until 10:15 if you want. So just now there's one question here. If you want to rest or you want to revision, also can. Maybe we start 10:15 later. So there's one question just now. So is R true a subspace of R3? Right? Okay, is this R2? Okay. So you can see that they are not even a subset. Right? Because the thing in R2, you write it as x1, x2. But the thing in R3, you write it as x1, x2, x3. Okay? So it is not a subset. But we have a concept of R2 sitting in R3. Okay? There are three ways to sit in R3. So we can include it as S1, S2, 0, or x1, 0, x2, or x or 0, x1, x2. Okay? We have different way of include it into R3, but it is not a subspace of R3. Okay? When we say this is like how we imagine a plane sitting inside 3D. Okay? So one of them is you sit as, so let's say E1, E2, E3. So one of them is sit as E1, E2 plane. The other is E1, E3 plane. The one is E1, E2, E3 plane. Okay, so either you are like this. Can I draw it? So let me like this. One of it is like this. The other one is like, okay, I should draw like this. Let me redraw it. So one of them is you can imagine sitting like this. Okay. The other one you can imagine it sitting like this. Okay. And one more you can think of it like sitting like so one is like this. Okay. E1, E2. E1, E3 is like this. E1, E2, E3 is like this. But you can see the difference here is, you see, we always have is an element in R3 when you want to speak about subset. You cannot start with anything. So there's another thing is when we talk about subspace, right? So subspace, you must say subspace of what vector space? Okay, of a vector space. So you need to tell me what vector space, subspace of what vector space? Okay, subspace of a vector space. You cannot just say subspace. Okay. Similarly, for column space, row space, null space. So of what? Okay, of a matrix. Okay, we only learn for matrix for now. Actually, there's a definition for general vector space, but for now we only learn for matrix. But when we talk about column space of a matrix, because we want to take out the column vector. Column space, row space of a matrix, because we take a linear combination of the row vector. Null space of a matrix, because we take a matrix, multiply elements in the null space, we get 0. Okay. Okay, I think we should start now. So I need to get the first person in the for group to count and then come and report and then get the quiz from me. So every first person in the group, count how many people inside your group and then come and quiz. You can use calculator if you need, but you cannot use iPad, from laptop, or from electronic devices. 23. Yeah. 14. Oh, 这边. So if you need draft paper or more paper, you can ask from me. Don't start first, but you can read. So you can turn off your phone, shut down your computer, laptop, keep them away. Why got 3 more left? So weird one. Then the 3. You have only just 1 left. So I put the inverse, not enough. The inverse question on the first part here because you can write to the last page if you need. Okay. In question 4, you don't need so many space. bet there's one more doesn't have it's enough. Don't start first, you can read. Write down your name and student ID. Is it enough? Okay. Enough. So weird. Okay. So write down your name and student ID. So what time is it? So it's 10:16. So we'll start now and end at 10:46, 30 minutes. Last question, right? Don't just put yes or no. Reason why yes, why no. And the reason should be short. Looks left. You're done. Check your answer. Check your name, student ID. Okay, time's up. So check your name, student ID. Please pass it to the front. Just open up and then compile it as a group. So I get four sets. Okay, pass to the front. So the front person, please help me to count again. Make sure you got the same number you got just now. Open up, pass to the front, and then help me compile as a for group.
说一下。
To the front. So, I want to know who is Son Tianzi this time. Where? Okay, you. Okay. Nice to meet you. If there's one more haven't take quiz, if she managed to take the quiz tonight, then hopefully I will finish by tomorrow and I give you back. Otherwise, we need to wait until next week. If you haven't got your quiz from last week, you should contact me. You can contact me and I can take a photo for you and email you. So please email me if you want to see your quiz. All right, see you tomorrow. Thank you for your cooperation.
再拿一个好吗？这个，等我。